All right, so that brings us to rationalizing denominators with two terms. All right, so you remember this example a couple sections back, we multiplied the square root of 3x plus 2 times the square root of 3x minus 2. Let's look back at that example right now. Square root of 3x plus 2 times the square root of 3x minus 2. So this would be a great one for you to try. Pause the video, try it, come back, we'll compare notes. All right. So you could FOIL this one, and if you did it that way, that's perfectly fine. I am going to do it slightly differently because I notice that there is a special pattern going on here. This fits the pattern A plus B. This fits the pattern A minus B. And what did we learn way back in the day about A plus B times A minus B? We learned that it multiplies to A squared minus B squared. So instead of foiling, there's a little shortcut. I'm going to write this as the square root of 3x squared, and then this will be 2 squared. All right, so what is this? What is the square of the square root of 3x? We should make that into another important concept. I'm going to write concept up here. Well, the square root of 3x squared is just another way of saying square root of 3x times square root of 3x. And that's the same concept that we had before. That would just be 3x. Okay. So understand that you are sometimes going to see it in this form, the square root squared. It's basically that the square and the square root just cancel each other out. So that comes out to A. Okay. This cancels with this. You can think of it that way if you want to. So this would simplify all the way down to 3x minus 4. And try to keep that one on the back burner. I have a feeling we might be seeing that again. All right, so what we're going to do to rationalize the denominator of 1 over the square root of 3x plus 2, using that example that we just looked at. Since we know that multiplying the square root of 3x plus 2 and the square root of 3x minus 2 will give us an expression that doesn't have any radicals in it, we should multiply the top and the bottom of this expression by the square root of 3x minus 2. All right, because as we just remembered, the square root of 3x plus 2 times the square root of 3x minus 2 gives you 3x minus 4. So that denominator is rationalized, and again, we don't care about the numerator. The numerator happens to be the square root of 3x minus 2. All right. So I think all that's left to do at this point is grab our examples, which are right here. And I see that one of these examples is the one that I grabbed from calculus. So this is the kind of rationalizing the denominator that we do in early on in first semester calculus. All right, so let's do these examples. All right, so the first one was 3 over the square root of 7, subtract 4. All right, and by the way, when you have two expressions, they kind of look like binomials, and the only difference between them is the sign in the middle, like the square root of 7 subtract 4 and the square root of 7 add 4. Those expressions are called conjugates. All right, they're not exactly opposite. Well, they're not opposites. They kind of look like opposites, except if they were opposites, all the signs would have to be opposite. So in this case, it's just the sign that's in the middle. And of course, whatever you do to the bottom, you have to do to the top. So let's stick with that color. And again, the whole reason this works is because this has the form a minus b. This has the form a plus b. When you multiply an a minus b and an a plus b, you get an a squared minus b squared. So in this case, that would look like this. The square root of 7 squared minus 4 squared. And we'll talk about that in a second. Upstairs, we have 3 times the square root of 7 add 4. All right, so when you square the square root of 7, you just get 7. When you square 4, you get 16. Upstairs, we have 3 times square root of 7 add 4. 7 minus 16 is negative 9. Okay, so what I would do with this, and it doesn't really matter too much how you get there, that 3 over negative 9 can be simplified. And what I would do is I would divide them both by negative 3. 3 divided by negative 3 is negative 1. Negative 9 divided by negative 3 is 3. So what that would give you is negative square root of 7 add 4 over 3. And there are probably a couple of equivalent ways to write that. That's how I would write it. Just make sure there's a negative sign somewhere. All right, next we have this ugly thing. So we want to rationalize the denominator. So we're going to multiply the top and the bottom by the conjugate of the denominator, which would be 2 square root of 5 plus the square root of 2. Okay. Thinking about it now, I kind of wish that I had left another blank slide for this afterwards. So I might have, when I get to the bottom, I might have to erase the top. You've seen me do that before. Again, this has the form a minus b. This has the form a plus b. So when I multiply those together, I'm going to get an a squared. Let's not write it there, though. I am going to get an a squared minus b squared. All right, so we're going to square 2 square root of 5, and then we're going to square the square root of 2. All right, upstairs, we're going to get something kind of awful. We're going to end up foiling this. 4 root 5 plus root 2 times 2 root 5 plus root 2. Okay, so let's get started. FOIL. All right, 4 root 5 times 2 root 5 would be 8 times 5. Think about that for a second. 4 times 2 is 8. So 4 times 2, and then root 5 times root 5 is just 5. The outer would be 4 root 5 times root 2, which would be 4 root 10. The inner would be root 2 times 2 root 5, which would be 2 root 10. And then last would be root 2 times root 2, which is just 2. All right, downstairs. The square of 2 square root of 5 would be 2 squared, which is 4, times square root of 5 squared, which is 5. And then, of course, the square root of 2 squared is just 2. All right, actually, I think we will get most of this done on just this slide. So now we have some like terms to combine. I see this 8 times 5, which is 40, add 2 will give me 42. And then 4 root 10 plus 2 root 10 would be 6 root 10. And then downstairs we have 4 times 5, which is 20. 20 minus 2 is 18. All right, so there's one more little thing I can do to this. I can simplify this a little bit because 42, 6, and 18 are all divisible by 6. So if you factor a 6 out of the top, that leaves you with 7 plus root 10. And then downstairs, 18 is 6 times 3. So these 6s are going to disappear. And I think I just barely have enough room to write the answer. It's going to be 7 plus root 10 over 3. All right. Taking a deep breath. All right. And going to the last example. The calculus example. So in calculus, we study something called limits. And what we would be interested in for this problem, notice that this expression is undefined when x equals 7. And that's because if you look at the denominator, 7 minus 3 is 4. The square root of 4 is 2, and 2 minus 2 is 0, and you can't divide by 0. The question in calculus, though, is what does this expression do near the number when x is close to 7, when x is like 6, 6.5, 6.9, 6.99, or 7.1, 7.01. All right, very, very important concept in calculus. To get at the answer to that question, you rationalize the denominator, and then what ends up happening is you get an expression that you can evaluate when x is 7. So I'm going to multiply the top and the bottom by the conjugate, which of course is the square root of x minus 3, add 2. All right, so what does that give me? Here's an a minus b. Here's an a plus b. So they're going to come together and give me an a squared minus b squared. So we're going to have a square root of x minus 3, and then we're going to have a 2 over here. Upstairs, I'm just going to leave this as x minus 7 times the square root of x minus 3 add 2. All right, so when I square the square root of x minus 3, I just get x minus 3. And when I square 2, I get 4. I see something kind of magical about to happen. All right, what is x minus 3 subtract 4? Well, it's x minus 7. Oh, and I'm excited about that because we have an x minus 7 on top. This is the kind of thing that tends to happen when we do this problem in calculus. Stuff starts to cancel. All right, so goodbye x minus 7. That just leaves us with the square root of x minus 3, add 2. So now if I was still wondering, what does this expression look like when x is close to 7? Well, now I can plug 7 into this new expression, and 7 minus 3 is 4. The square root of 4 is 2. 2 plus 2 is 4. All right, so it means that the original expression when x is near 7 would be close to 4. Okay, so I hope those of you who are going on to calculus might think about this day when you get there. All right, we're almost done. One last thing that we're going to look at for just not long at all is rationalizing numerators. So you don't see this done as often. There's not as often a need for this. However, there are certain problems, again, in calculus sometimes where you need to rationalize the numerator. The good news is there are absolutely no new tricks to it. So I'm just going to show you a couple of examples, but it's going to be all the same tricks that we've been using all along. So starting with the square root of 3x to the 5th over 6, the first thing I would do is simplify that radical. There is a perfect square factor x to the 4th hiding in there. 3x would be a leftover. I break that x to the 4th out, it becomes x squared. Okay, so remember I'm rationalizing the numerator. So that means multiply the top and the bottom by the square root of 3x. And that would give me my original x squared times the square root of 3x times the square root of 3x, which is 3x. And when you're rationalizing numerators, you don't care what happens to the denominator. The denominator will almost always end up with a radical in it. Can't be helped. Okay, most of the time, you're going to have them one place or the other. Okay, and while I'm here, I notice the 3 and the 6. Let's divide that by 3, divide that by 3. So we're going to end up with x squared times x, which is x cubed, over 2 times the square root of 3x. All right, and then finally, the cube root of 25 over 2. So the first thing I'm going to do, as usual, when I have a whole entire fraction under the radical, is I'm going to use my quotient rule to split that up. I'm also going to write this 25 as 5 squared. Okay, because since this is not a square root, this is one of those cases where we're going to have to think about making the radicand a perfect, in this case, third power. So we need that radicand to be 5 to the third. All right. And how we're going to do that is we're going to multiply the top and the bottom by the cube root of 5. Right? We already have 5 squared. We just need one more 5. All right, that's going to make our denominator cube root of 2 times the cube root of 5, which is cube root of 10. And the cube root of 5 cubed is just 5. So final answer, 5 over the cube root of 10. And that's going to do it for section 10.5. We'll see you next time.